In the next few videos, we're going to be taking a look at some of the basic MOSFET applications. The first one we're going to consider is amplification. And so we're going to come back and we're going to cover this in a lot more detail in the next unit, but the basic idea is the same as what we saw with our bipolar junction transistors. So here we have our DC Mosfet circuit. So this is similar to what we considered previously. So we have this voltage divider biasing network with R1 and R2. We have our drain resistor, and we have an enhancement mode in-channel MOSFET. So what we can do is if we have some small signal voltage, let's say that we want to amplify, we can capacitively couple that to the input the same way as we did with our BJT circuit. So lowercase v, lowercase I to indicate this is a small signal voltage, and I can connect that with a coupling capacitor. And so remember, the coupling capacitor is going to appear like an open circuit to DC signals and a short circuit to AC signals. So we want to choose a value of that coupling capacitor that is appropriate based on the frequency of our AC signal. And then I can define my output as being at the drain. And depending on our amplifier configuration, our input and output might be at different places. And again, that's what we're going to come back to a little bit later. Now, I think it's easiest to see the process of this amplification if we consider the load line. So remember, our DC portion of the circuit right here is very important, as that's going to set our operating point or our Q point of the circuit. So if we come down here to our load line, we see based on, for this particular circuit, our maximum current is going to be VDD over RD, and our maximum drain to source voltage is going to be VDD. And so I can determine that just by doing a KVL along our drain source path over here. And I've superimposed this on top of a few of the family of IV curves. Remember, we can always add more. This is a continuum, not necessarily just discrete curves. But let's say we have R1 and R2 chosen such that, and RD as well, such that our Q point is right here in this center curve. And so we can say that this Q point, so let's go ahead and label that as our Q point, corresponds to some VGSQ value. And so of course we're also going to have some VDSQ that corresponds to that. So this would be our VDSQ, as well as some IDSQ, which I've drawn this so that there's essentially no slope in that saturation region. So that's going to be about the same value there. So that would be our IDQ. And so the same is what we saw for our BJT amplifiers. If we want to have linear amplification, we want to make sure that the device is staying in our saturation region. So for linear amplification, we want our MOSFET to stay in saturation. And so, of course, if we move our Q point too far on towards this end of the load line, we risk turning the device into cutoff as we see small signal swings in that Q point value. And if we move too far to this end of our load line, we're risking going into non-saturation, or our triode or ohmic region. And so we want to stay out of those two other regions if we want to have linear amplification without clipping. So what we could say is maybe we have some input signal which is causing our gate voltage to vary between these two other blue curves that I've shown here. And so really they should be equally spaced from that center curve, but I've drawn it a little poorly so they're not quite center spaced. But let's say our VG is varying between some VGS plus and VGS minus. And so I've drawn sort of a sinusoidal wave superimposed on top of that. Well, of course, that's going to correspond to changes in our ID as well as changes in our VDS. So we would have our ID varying here between IDQ plus and IDQ minus, and similarly our VDS would also be varying between these 2 points. So we would have some VDS minus and VDS plus. So very similar to what we saw previously in terms of our BJT amplifiers. And again, we'll go over this in a lot more detail in the next unit.